Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We will now discuss the solution of a problem that appeared in the CSIR National Eligibility Test held in the month of July 2024. This question is from the section Linear Algebra and it is related to the concepts of eigenvalues and eigenvectors. This question is from the part C, which is a multiple select question. There can be more than one answer and it carries 4.75 marks. The question ID is 704073. This question is suitable for the aspirants of JEL, DL, TS set, AP set, IIT JAM and GATE. Right. The given question is, let T be a linear map from R power 4 to R power 4 with 4 distinct eigenvalues. So T is a linear map from R power 4 to R power 4 with 4 distinct eigenvalues satisfying T power 4 minus 15t square plus 10t plus 24i is equal to 0. Which of the following statements are necessarily true? We are given 4 options. Option 1. There exists a non-zero vector v1 belongs to R power 4 such that tv1 is equal to 2v1. Option 2. There exists a non-zero vector v2 belongs to R power 4 such that tv2 is equal to v2. Option 3. For every non-zero vector v belongs to R power 4, for every non-zero vector v belongs to R power 4, the set consisting of 2v, 3 times tv is linearly independent. Option 4. T is a 1-1 function. Right. We will now discuss the solution of the problem in detail. That's the given question, the hypothesis of the question, and we'll now discuss the solution. We are given T from R power 4 to R power 4 is a linear map and it has 4 distinct eigenvalues. This is a very important hypothesis condition given to us. The linear map has 4 distinct eigenvalues. Agreed. And it satisfies this equation. T power 4 minus 15t square plus 10t plus 24i is equal to 0. Can we conclude that x power 4 minus 15x square plus 10x plus 24 is equal to 0 is the characteristic equation of this T? Can we conclude? To conclude that one, the given condition that it has 4 distinct eigenvalues is very important. How do we go about it? So, since T has 4 distinct eigenvalues, we consider its minimal polynomial of T, mt bracket x. And this minimal polynomial of T also has the same 4 distinct eigenvalues. Yeah. So the eigenvalues of T are also the eigenvalues of the minimal polynomial of T. So because t has 4 distinct eigenvalues, the minimal polynomial of t also has the same 4 distinct eigenvalues. This implies degree of the minimal polynomial of t will be 4. Right. So now the minimal polynomial of t itself is the characteristic polynomial of t because the dimension of r power 4 over r is 4. Right. So the minimal polynomial itself is the characteristic polynomial of t. That means they coincide. Given that t satisfies this equation, p of x is equal to x power 4 minus 15x squared plus 10x plus 24 is equal to 0. That means t annihilates this polynomial. Therefore, p of x is an annihilating polynomial of t. Recall a result. Recall a result. The minimal polynomial of t always divides every annihilating polynomial of t. So, the annihilating polynomial of t divides p of x. Now, the minimal polynomial of t is equal to p of x. Why? Because the degree of p of x is 4 and the minimal polynomial of t divides p of x and mt bracket x is monic. Is a monic polynomial. For that reason, mtx divides p of x will give you mtx is equal to p of x. So that means p of x is equal to 0 is the characteristic equation of t. So that's the proof to get the answer that p of x is equal to 0 is the characteristic equation of t. We continue in the next slide. We have p of x. This is the p of x is equal to 0 is the characteristic equation of t. So let's call option 1. There exists a non-zero vector v1 belongs to R power 4 such that t of v1 is equal to 2v1. So yes, this is possible. This is true provided 2 is an eigenvalue of t. Let's see. Note that p of 2 is 2 power 4 minus 15 into 2 square plus 10 into 2 plus 24. Simplify. You will get that is equal to 0. P of 2 is equal to 0. That means 2 is an eigenvalue of t. When 2 is an eigenvalue of t, there always exists a non-zero vector v1 not equal to 0. That is precisely the eigenvector such that t v1 is equal to 2 times v1. Right. Right. So that's our option 1 is true. Let's call our option 3. Yes, that is convenient for us now instead of option 2. Option 3. For every non-zero vector v, here the catch is every non-zero vector v belongs to R power 4. The set consisting of 2v, 3tv is linearly independent. Now, from the option 1 above, there exists a non-zero vector v1 belongs to R to the power of 4 such that tv1 is equal to 2v1. So, we have a non-zero vector v1 such that tv1 is equal to 2v1. So, take that v1 and take the set 2v1, 3tv1. So 2v1, 3tv1, that is the set. That will be 2v1, 3 into tv1 is 2 times v1. So 3 into 2v1. So 2v1, 6v1. That set is linearly dependent. Why? 6v1 is 3 times 2v1. 6v1 is a integral multiple of 2v1. So this set is linearly dependent. But here is a v1, non-zero vector v1, for which this is linearly dependent. So therefore, the option 3 says for every non-zero vector v, this set is linearly independent is not true. So thus the option 3 is not true. Now let's go to the next slide, and we now call on our option 2. There exists a non-zero vector v2 belongs to R power 4 such that tv2 is equal to v2. This will be true provided 1 is an eigenvalue of t. So assume that it is true. If you assume that it is true, 1 is an eigenvalue of t and v2 not equal to 0 is the corresponding eigenvector. Now the question is 1 an eigenvalue of t? Let us test it. P of 1 is equal to 1 minus 15 plus 10 plus 24. That is the sum of the coefficients of this equation, which is not equal to 0. This will tell you 1 is not an eigenvalue, a contradiction. Therefore, our assumption that it is true is not true. Therefore, the option 2 is not true. Right. We move to the last option. T is 1 to 1. For this, we recall a theorem. The theorem is, let V be a finite dimensional vector space over a field F. T belongs to A bracket V. That is, A bracket V is the vector space of all linear transformations, linear operators T on V. So T belongs to AV is invertible if and only if the constant term of the minimal polynomial of T is not 0. Do we know the minimal polynomial of T? The minimal polynomial of T is same as P of X. In the P of X, the constant term is 24, which is not equal to 0. Apply this theorem, then T will be invertible. When T is invertible, T is bijective. Therefore, T is 1, 1. Therefore, option 4 is true. Now, the constant term of the minimal polynomial of T, that is equal to P of X, is equal to 24, which is not equal to 0. By the above result, this result, T is invertible. This implies T is bijective. Therefore, T is 1, 1. Thus, our option 4 is also true. So now, summarizing all the options, the answer to this question is option 1 and 4. That is the detailed discussion of the solution of the given problem from the section linear algebra, which is based on the concepts of eigenvalues and eigenvectors. It is definitely a very good question. I am sure that you understood the solution of this problem. I thank you all for watching my videos. Please like my videos and share them with your friends and colleagues, and subscribe my channel if you have not already subscribed. I wish you all the best. Thank you.